we will welcome you to the second class, module 1 on the virtual classroom course on dynamics of ocean structures. So, in the last lecture we started to discuss about various types of offshore platforms. It is very important for us to know that how these platforms are categorized, how they are classified, because the dynamic analysis of these platforms actually depend upon the category of the classification. So, in the last lecture we quickly saw that one type of platform which is having a fixed base and just to recollect that we said these platforms are very stiff, as a result of which they attract more forces. So, it is very important for us to know that depending upon the classification of the platform, how structurally the platform is going to behave, what will be the inbuilt dynamic characteristic of the platform because of its geometric configuration, because these two factors become very important for dynamic analysis. So, we are talking about this when we speak about the classification of the platform as such. So, we will again continue to discuss different types of ocean structures in this lecture as well. We will have one more lecture on this subsequently. If we talk about fixed type of platforms, we already said the base of the platform is fixed to the seabed, structure is very stiff, what I assume as rigid in my analysis, it tend to attract more forces, response to wave loads is relatively less, but the structure is expensive, it has its own problems related to this covering of seabed, etc. Very importantly, these kinds of platforms were very popular in the early stages, but now they are practically obsolete. You do not have these platforms now ever attempted to be constructed because of a very simple reason: these platforms cannot be placed at deep waters. It means water depth is also now playing a role in selecting the geometric configuration of offshore platforms. It is very interesting for us to know that offshore structural system is one amongst the unique system which is governed by the location where it is being installed. So, if you compare this for any other kind of similar structures like bridges, like land based buildings, like tall buildings, schools, any other functional building, even monument structures, you will note only the substructure may have a variation in method of the foundations, etc. Whereas in offshore platforms, accordingly even the superstructure will also change. So, that is a very interesting problem, because once I have a change in the whole structural system, substructure and superstructure as well, the mass of the platform changes, and mass becomes a very important identity for my dynamic analysis. So, we have attempted to see two things: one, how mass is getting slowly focused in the platform geometry. We also saw how stiffness is getting focused in the platform geometry. So, in dynamic analysis we assign this with the notation mass. I am putting a matrix symbol because it depends upon how many degrees of freedom you are assigning the mass to. We will talk about this slightly later. I also put again a matrix symbol for stiffness K. These are all system international symbols and notations. M stands for always mass and K stands for always stiffness. We will talk about the units, how to arrive them, how to derive these for different platforms later, but slowly the focus is getting towards two important characteristics of dynamic analysis, which is mass. Mass is of course a combination of substructure and superstructure, and superstructure will have more added values because of topside configurations, which I will show you in the next slide. So, mass gets altered depending upon the placement of depth of water. Stiffness gets altered depending upon the functional characteristics of the platform. Therefore, in dynamic analysis of ocean systems, you do not have any control to play with these characteristics, because it is not function driven, it is form driven. What do you understand by form driven and what do you understand by function driven? I can give a very simple example. I want to design, let us say, a drawing room. The space of a drawing room may be rectangular, may be square, may be having a curvilinear profile. So, you do not find much variation in the form, but the functions of a drawing room can be different. So, what we try to do in general design is form dominates the function. So, in this case I am not interested about the function driven, I am focusing on the form driven, because form will focus at what depth I should install what kind of platform, whether the platform should have a fixed base, whether it should be compliant and floating type, should it be a semi submersible, should it have enough buoyancy, should it be neutrally buoyant, should it be positively buoyant, all are essentially derived from the form, and form will control the mass and methodology of installation will control the stiffness. So, it means in dynamic analysis of ocean systems your major focus is not on the characteristics of the system, it is essentially from the form of the system itself. That is why generally in offshore design systems your design and selection of the platform type matters a lot. If you look at this comparison with analysis of any other structural system, maybe shell structures which is also form driven, maybe any other rectilinear plan buildings which are onshore based systems, you will first select the form which is more or less standard, function is not seriously altered, and dynamic analysis becomes more or less categorically simple, except for the configuration problems in the substructure. Depending upon the foundation system, you may have some complexities in the dynamic analysis when you include soil structure interaction in land based systems, whereas in dynamic analysis of ocean systems you start the complexity in the beginning itself by choosing a form. Itself is a complexity. So, we must understand which form should I choose for what kind of installation. So, these two lectures will give you a feeling that what are the different forms constructed elsewhere in the world, how are they structurally behaving under the environmental loads, and from that we will derive the important characteristics of mass and stiffness, and furthermore characteristics I will follow in the coming lectures. How do we derive them? Any questions here? So, we must appreciate that why ocean structural systems or offshore structures in general tend to become unique not only in construction and installation, but also in analysis and design. Okay, we do not have much of a choice, we select or choose a form for a specific requirement which is of course functional based, there is no doubt. For example, the platform selected for drilling which is exploratory may be different from drilling which is productive. So, there is a functional component in the selection of the platform, there is no doubt on that, but that is not dominated, because my platform geometry will get dominated depending upon where I am installing it. What I am using it for becomes secondary, whereas in any other design if you see function slightly dominates the form, or there is a close coupling between these two, but in ocean structural systems it is slightly deviated. Therefore, dynamic analysis of these structural systems becomes more interesting and more challenging. Is that clear? Any questions here? So, you will see that every form which is being selected for different applications should not, will not look alike, because every form will have its own problem. When people analyze it, when they reconstruct another structure of a similar form, they do make alterations. That is why you do not find repetitive designs and forms in offshore structures, because every form is site specific, it is not function specific. Okay. So, that makes the difference, therefore, they are unique. So, let us quickly look at some of these photographs of the forms. So, these are some of the platforms constructed elsewhere, the deepest and the shallowest. You will see obviously all of them are in United States, the deepest one. The maximum depth for a fixed base structure has gone till 400 meters approximately, whereas the shallowest platforms were not located in US in the later part of it. So, we will see all the photograph of two of the platforms. A Bullwinkle platform we must have seen, it is an open source literature. It is located in a Manatee Field, Gulf of Mexico, approximately 260 kilometers of North Orleans. The cost of this is about $500 million US. Heerema Marine Contractors built it at a water depth of about 412 meters. Total height of the platform is about 530 meters. All these dimensions will be very amazing. If you compare this to any land based system, it is as good as about 120 story building, because if you look at the building height is about 3.6 meters, approximately 4 meters, let us say, to make it easy 5 meters, it is close to about 120 story building, which is an amazing structure when it is land based. Okay. So, it is all not very unusual constructions, they are all unique in its dimension, in its location, in its function, and of course in its cost also, because they are very highly priced. So, built in the year 1988, it takes about 3 years approximately to commission a platform. The weight is about 77,000 tons, it is a very heavy mass based system as far as fixed platforms are concerned. So, I want you to understand the evolution of how the platform mass moved from a heavy based system to a floating based system, and why it was moved, what was the reason. So, 77,000 tons is really a tremendous mass for any structural system of this order. It produced about 59,000 BOPD. So, there is a clarification here required for all the ocean engineers or offshore engineers to understand what is BOPD. BOPD is the barrel produced per day, and one barrel is approximately equal to about 160 liters. So, that is the amount of oil being produced in one day. Then understand the value of the reserve which this platform generates. If you look at it in the present cost, it approximately comes about $7 million US. If you look at the cost of the oil today in the international market, the revenue generated by this platform is $7 million US in a day. That is why they could invest around 5,000 million US to construct this platform. Okay. The revenue is very high, phenomenally high, cost of construction is very high, they are therefore unique. That is the reason why these platforms are not constructed very often, they are very rare. So, they do extensive survey to carry out the detailed analysis, then they construct such platforms. They are not always constructed very often, they are very rare. Okay. That is why you have seen the last slide, we have got only about 5,300 odd platforms all over the world. It is not important how many of them do we have in India, but in general we are talking about the perspective in the international scenario. Okay. So, this example will give you an idea that what is the material being used in this kind of construction. What is the material expected to be used in this construction? Steel. So, other characteristic actually comes from here is a third one. you may wonder why I am talking about material in dynamics. So, material may be interested for construction technology, construction management and practice, cost management, etc. I am talking about material because I am going to derive a very important concept from material, which I am going to say damping. So, which is of course an important characteristic in dynamic analysis, which is indicated by C. There are varieties of damping, material based damping is also important for us. When I talk about nonlinear dynamic analysis, which I will speak in the later module, when I say nonlinearity, it is essentially a material dependent characteristic. So, I must understand, can the material become nonlinear under the given forces? Can I stretch it to a nonlinear regime? I must know this. So, essentially the material what you see here is steel. So, it is not essentially always it has got to be steel, there are other material also coming up which I will show you, because the moment you say steel is my only material possible for this construction, then I cannot compensate on mass, because steel density is fixed. But if you want to compensate on mass to make it floatable or afloat, then I must have a material which actually floats or whose mass is relatively lesser. So, when you talk about form driven design or choice, I have to work on mass. The moment I say material is only steel, then I have no option. That is how the evolution of platforms started actually. Initially it was on steel, even now steel platforms are constructed, but there are other material also playing role. So, material selection is also important in dynamic analysis indirectly for me when you talk about damping characteristics of the material, and nonlinearity if I wish to do a nonlinear dynamic analysis. Any questions here? So, there is another platform which we have, Pompano platform is another example, classical example of a fixed base structure. Water depth about 400 meters, 4 leg 12 pile system, constructed 1994, 38,000 tons weight, 60,000 BOPD, and of course volume of gas. Hibernia is a gravity based structural system which is GBS platform. You can see now the foundation system has slightly altered with respect to the previous platform, okay, Hibernia platform. Here this is a classical example of gravity based structure. This is another fixed base platform which I call so the name itself suggests that the structure is having a very high volume of mass, very high value. So, it has got to rest on the seabed or its self weight, that is why we call this as gravity based structure, which is also a fixed base. It may not require a pile foundation, located in Canada, 80 meters. So, you can understand that when I go for a huge mass system, the depth wherein I can put is reduced. When I go for a light mass system, I can go for a depth at a higher water depth. It means there is a proportion which is connecting water depth where you are going to install to the mass of the structural system which you are selecting. Okay. So, this indication what we learned from these 3 examples very simply, that when I go for deeper and deeper, I can go for mass of a lower value. When I go for a higher mass, I cannot afford to build it at a greater depth. The essential reasons are 2. One, of course, the cost. The moment I say cost, it is not the cost of construction or the material, it is the cost of installation, decommissioning, all. As I said, in offshore platforms we do not bother about the cost much, because when I find the oil reserve, then cost may not be very important. But why I am talking about the cost here indirectly is that it causes other serious problems. For example, seabeds cover. Seabed erosion, it causes differential settlement. It affects navigation. So, these are all serious problems as far as massive structures are concerned. One such example is gravity based structure, which you see here. It is an Hibernia GBS platform. You can see the weight, constructed 1997, 50,000 BOPD and so on and so forth. Troll platform constructed in Norway. You can guess what type of structure is this. So, again the top side is essentially the steel, whereas the pile, foundation, etc. substructure is essentially concrete. Interestingly, ladies and gentlemen, 1996 this platform has set a Guinness World Record. Okay, this was considered to be the largest offshore platform then in 1996. So, offshore platforms are not only unique, they are also in the Guinness Book of World Records, okay, because of its capacity, size, installation, many reasons, not of course because of the cost. Okay, you cannot record it in terms of cost. Any reason why we are not able to actually award a Guinness record based on the cost index? What is the reason? For example, I have a pen which is unbelievably, let us say 1 crore or 100 million US dollars. Can it be considered as a Guinness Book of World Record pen because it is so expensive? Why cost index not considered as one of the parameter to evaluate the Guinness Book of World Records, for example? Why? Size of course is there, as becomes smaller and smaller it can get a name in the Guinness Book of, as larger and larger it can get a name in the Guinness, but cost is never been indicated because cost cannot be normalized in different currencies all over the world. Okay, it cannot be normalized, it fluctuates every hour, every minute it fluctuates actually, that is depending upon the economical situation of every country. So, Guinness Book of World Records is an universal parameter which has got to be normalized about all the countries, so it cannot be done, right. So, cost factor is not important here, it is considered as largest offshore platform. So, total height about 472 meters, volume of concrete, we know the density of concrete. What is density of concrete, by the way? Density of concrete, plain cement, okay, reinforced cement concrete. I think it should be one at a time, no, otherwise people will take benefit of doubt. $2,500 or 25,000 kg per cubic, let us put it like this. So, largest platform, Guinness Book of World Record, gravity based system, very high volume of concrete and of course very high volume of steel being used in this. So, you see the construction here. The second type of platform which is commonly used, which is also a fixed base, is steel jacket structure. Steel jacket platforms, the name itself suggests the material. The top side is referred, the superstructure is generally referred as a top side. It supports lot of equipments which are being given here as drilling equipment, production, gas turbines, generating sets, pumps, compressors, gas flash stack, revolving cranes, survival crafts, helipad and living quarters. One may wonder that why we are interested in talking about these details in dynamic analysis. Now, the mass will have elements contributed from different sources. One is from the self weight of the material, which depends upon the geometric dimensions of the member and of course the density of the material. The second can be the live load or superimposed load which is being caused by some of the operational equipments which are seen on the top side here. The third could be the vibration interface when these equipments are under operation with respect to the dynamic analysis of the original structure. So, we must know the characteristic of at what speed, at what velocity or at what acceleration the pump will operate, what will be the operational temperature, pressure and speed of the compressor, what will be the weight, where is it geometrically located with respect to the CG of the platform, all will cause influence on dynamic response behavior of the platform as such. So, it becomes important. Parallelly we can compare, if you want to design a water tank, the dynamic analysis of water tank with and without water are different. When the tank is empty, the characteristics are different or the response behavior is different. When the tank is getting filled, it is different. When the tank is full, it is different. While discharging and loading, again the behavior can be different. What we call as sloshing effect, slamming effect, which will be actually one of the influence caused by the liquid on a container. So, similarly here we are looking for the interface. So, we should know what are those components that are available. So, if you are looking for any problem where you are going to design a new form of the platform, as I said, depending upon the water depth, your research may be focusing on a new type of an offshore platform which may be suitable for a depth of 2000 meters. You will select a form. For the form, you will select some functional requirements from the equipments. So, which equipment you will allot there, where and why. So, we must have an idea about this. Though remember very carefully that we are not going to do dynamic analysis of all of these things independently and then do a coupling analysis with the platform, that is not in the scope of this course at all, but we must have an idea that the top side of a platform is not a blunt area, it is having lot of electro mechanical process equipments complexly located on the top side. The interface makes a difference. Okay. So, our focus is only on that particular point. So, this is basically a schematic view of a jacket like structure which you must have seen if you are a naval architect or ocean engineering student. For the benefit of other viewers also, let us see there is an important schematic view of a jacket like structure. The pointer is not working, so I can point out here directly using the mouse. These are some of the important components which you must name. I will give these details in the next lecture, not because I do not have it here, I have it here. I want you to look at it once. So, I want you to self read it, what are the important components present on the top side in a simple jacket structure. So, they are suitable for water depths up to 250. People have attempted to build this at 350 meters as well. Depends on the wave climate. The jacket surrounds the pile and holds the pile extension in position in the soil, and the soil should be essentially a clay. It supports and protects the well conductors, pumps, etc. That is why the name jacket is being given. Jacket is always an enclosure. Yeah, I wear a jacket to enclose my body, etc. So, jacket is nothing but an enclosure. It is also called as a template structure because the jacket legs are used as guides for driving the drilling rigs in the template system. So, it is also called as a template structure. Soil condition suitable for this kind of platform is clay because you need the piles to be penetrated. It is not suitable for rocky environment. So, that is about the basic knowledge of where should I select a jacket platform and why. So, essentially the material predominantly used is steel. The substructure or the jacket is actually pile supported system which is bottom supported. Piles can be as large as 2 meter in diameter and they can penetrate as deep as 100 meters depending upon your soil condition. This again another figure which shows me the parts, either you can draw a line diagram of this and note down the parts, or I want you to look at some of the platforms in reality in photographs in the website and then identify the parts. We are not anyway interested in explaining these parts in detail as far as this course is concerned, this is not a part of this, but you must have a basic idea that why I am saying this, because a tailor who never wears a shirt cannot stitch a shirt. Okay. I have seen this in different countries, I have travelled at least good number of countries. I have seen one uniqueness in hair cutting in different countries. Hair cutting, we all agree that it is not a formal education. I do not think no barber undergoes an education how to cut an hair, except that in spas where people charge for the same hair manifold cost of the hair itself for dressing the hair. In fact, for losing the hair you are paying money, that is amazing. People pay money for gaining the hair, I agree. For losing the hair people are paying money in a manifold, that happens in spa, and earlier it was attached only to female sex, now males are also using this money. I mean I have seen many people who are going to spa and spending money unnecessarily on hair cutting. So coming to this argument of hair cutting which has no formal education, I have seen a uniqueness and a commonness in barbers who does hair cutting all in different countries where I have visited. At least I got haircut in many countries, of course at different prices. After he completes the haircut, which you have realized, all at least male members will realize, because it is very difficult nowadays to understand who is a male and female looking at the back, only the hair, okay, because they also have a long hair, very difficult, and female have a short hair, it is very difficult to identify. But after the haircut is complete, the barber essentially shows you the rear side of the view of the mirror, just to ensure that your back portion is perfect. This is, remember, it is a technical satisfaction to the customer. There is no formal education for this, okay. Every barber in every country does this. Similarly, another example, goldsmith. Goldsmith has no formal education, but the designs created in ornaments these days, though they are computer aided design, but manufacturing and articulation done in an ornament without a formal education is amazing. This has happened in construction industries in India also, as well as in Rome in Italy, for example Colosseum, for example monuments in Turkey, for example temples in deep southern India and Tanjore, etc. The architecture, the construction engineering was undocumented, unbelievable, because we have temples here in India whose shadow does not fall on soil, okay. The architecture is so nicely done, there are earthen dams, there are steel pillars which are non-rusting, so there are engineering which has been practiced, no wonder. But same ideas have become undocumentedly common in many engineering trade. So this has given strength to identify certain type of forms. So you may also be driven to select a new form on a research problem, there you must have an idea what are the complexities involved in the top side. So you must go through the details of these slides in an open source literature and try to understand what are the complexities in the top side, which is not going to be discussed here. So when we talk about gravity platforms, another type of platform which we said gravity based structural system, GBS platforms, the design objective is essentially for production. The salient features are the following: it has got a large reinforced concrete bottom, we all agree that why concrete has got to be reinforced, concrete is excellently good in compressive strength, but very weak in tension, okay. Now interestingly, a question which is very commonly posed to every structural engineer is this, let us see how you are able to react to this question when we talk about concrete as a design material. Concrete is very good in compression, but very weak in tension, bad in tension. it is a universal phenomena, people have understood this. But I have a column maybe circular, maybe rectangular, which is subjected purely to compression only, it is a column purely under compression, but I reinforce it. Why? It is subject to pure compression only, and concrete is excellent in compression. Why do I reinforce it? So, depending upon the point of application of load, the nature of load and combination of load, and major difficulty is erection or construction problems. Okay. There can be errors that the column may not become vertical, can become inclined. Okay. More importantly, with all the possible recent methodology of construction, still concrete is reinforced only to enhance the core strength, what we called as confinement effect. Okay. The confinement effect is very important. So, concrete is reinforced because of the following, but anyway gravity based structure essentially where concrete structures they use their own weight, self weight, to resist the environmental loads, and of course they are not attached to any piles, because they can rest on the sea floor directly because of their weight. They have been identified to be suitable for a medium depth up to about 350 meters, that is what the literature says, where people have constructed this kind of platforms. So, concrete has a base essentially of concrete. Interestingly, it is designed with lot of void spaces, which I call as caissons. I will show you a photograph next to this. Now, why this is important? A concrete structure which is having a lot of void space, functionally important because I want to store oil in that void space, or I can store some ballast material which can be used during installation and commissioning or decommissioning, agreed. But how we are connected to this void space is that the analysis of any structural system which has got a void space is different from that of a system which does not have a void space. So, in case of any structural system like a GBS platform which has got a void space in terms of caissons, it is important to do free floating analysis and dynamic analysis in place. Both are dynamic analysis. What we one is called free floating analysis, which will also be important because I have got enough void spaces, it will be governed by the buoyancy forces. When the same platform is resting on its position, then I have to do dynamic analysis because now the forces attracted by this platform will be different. So, it is important for me to understand free floating analysis, it is not free vibration analysis, I am saying free floating analysis, and dynamic analysis in position, because the load acting on the structural system in these two cases will be different. And very interestingly, you will now agree that all structures built except these examples what I am showing may not have to be done for all these kinds of analysis, they are not required, okay. But they become unique more in dynamic analysis sense that when you talk about offshore structural system, you must do both type of analysis to qualify them, whether to see the feasibility, whether they can be installed in a specific water depth under specific site conditions, etc. So, that is what the slide says. The void spaces, as I said, they are filled up for storage compartments of crude oil, or they can be used for filling up the material for ballasting, maybe water, maybe stone, etc., or an iron ore ballast. So, a classical example of a GBS platform, concrete gravity platform as at western coast of Scotland, constructed in late 70s, weighing over about 3000 tons, 300,000 tons. the time of construction it was considered to be the largest oil production platform in the Scotland region. These are all the void space of caissons which you see here. These are the void spaces. This is a tower, it rests on 4 towers. So the size of the platform is about 100 square meters, the height of the tower is about 56 meters, caisson alone, 56 meters, approximately 10 story or 11 story building, only the caissons. The towers are much taller than that, 116 meters. So you can imagine the total prototype size of this platform. Okay. They are not constructed once, they are in series. You can see at least 2 of them in the photograph here. One is in the towing stage, other is getting inside for the towing stage. The other photograph will show you when they are being towed off. You can use tugboats to install them. So it becomes important for me to understand the free flotation analysis also for any of these big form based structures, okay, which is a very interesting and exclusive demand in dynamic analysis for ocean structures. The third kind of platform what we see here is going to be a jack-up platform, or what we call jack-up rig, that is the third type. So we have seen platforms of 2 order, one fixed base, another is gravity based structure. Both of them are massive structures, larger in size but limited to water depth up to 350 meters. When you go for deeper waters, the platform model and the geometry or the form has got to get modified. So you see the jack-up platform here, you see the structural configuration of the platform is completely modified. You have only a simple hull essentially resting on 3 or pairs of legs which are essentially steel jacket systems. Why this is called as a jack-up rig? Because when the rig is not in operation, the hull which you see here will be kept at the lowermost position like this and you will float it. Once you reach a location, the deck is raised or the leg is put inside, that is why we call this as jack-up rig. Okay. The deck goes up and the legs get inside. It is a very interesting different kinds of platforms, jack-up rigs essentially, which are used for exploratory drilling and also for production drilling for marginal fields, not for large fields. Okay. They have a limitation. If you look at the accidental investigations of these kind of platforms, in general most of these platforms have failed not during operation, most of them have failed when they have been towed. So free flotation analysis for these kind of studies becomes very important, because literature show that these platforms fail when they have been towed from one position to another. Okay. There is a close view of a Massey Jain, which is a very famous jack-up rig shot in Singapore. The primary objective is for exploratory drilling, as I said. It is similar to the barge movement like a vessel. The rigs are towed down and the deck is raised up, that is why it is called jack-up rig. It is essentially recommended for shallow waters up to 150 meters. Now you may get confused, in the literature how do we define shallow, intermediate, deep, ultra deep waters? How do you define them? What would be the category, what would be the terminology, or what would be the parameters that will help me to define the water depth? There are many ways of assigning water depths depending upon hydrodynamic characteristics, depending upon choice of the platform you want. You say I am going to go for gravity based structure, therefore the depth where I install the structure has got to be a shallow water, and so on. But these definitions also keep on changing in the literature. Okay, it is not that standard that at 172 meter you call it a shallow water, at 172.1 it becomes intermediate depth. It is not like that. Okay, it is conveniently revised. Okay. So there should be an essential understanding for us to know what would be the classification. We will discuss this in the next lecture, and few more platforms we will talk about this in the next lecture. We will have one more lecture on types of offshore structural systems. Slowly at the end of these 3 lectures we must arrive are the basic standards of what are the different structural actions of different kinds of platforms. We will narrow down to that point. So, these 3 lectures will create the following objectives. 1, those who have not seen any such platform either in photograph at least has an opportunity to see it here, that is number 1. Number 2, people thought that offshore structures are as similar and as same as that of any land based structure. They are amazing structural systems, they are complex in nature, they are unique on its type, they have created world records as well. So, we must understand and realize that we are going to design or analyze a very unique structural system. Thirdly and most importantly, the whole exercise of oil exploration and drilling is getting into deeper waters because oil is not available in shallow waters. Therefore, every existing form of structure cannot be applied and used at deeper waters. It means there is a constant research happening in offshore industry that what kind of platform I must design for deeper waters. The moment you have this question in your mind, if you do not understand the dynamic characteristic of this platform behavior, you cannot design one of its kind. And believe me, no platforms which I have shown you here, all the 5300 platforms which are available now, none of a single platform will have the detailed dynamic analysis report in the literature, because they get patented completely. So, you will not come to understand how actually they have been tested and what are their intrinsic behavior under environmental loads. It is not disclosed. So, you have no database to understand how they have behaved or how they are behaving under the wave loads. So, essentially you must create an analytical model of this, try to understand the behavior, simulate it and understand it. Therefore, mathematical modeling of these structures becomes important for us in understanding point of view. Form driven structures becomes important for me in research point of view, and of course understanding them line by line is important for examination point of view.